Yes.
Okay, so we want to
Yes, sir.
revise. We want to really revise some of the things I taught in class, not just revising to, but we missed one class. I mean, the last week, which was a tutorial week. I wanted to come and teach, but for some reasons, you guys were not available or you canceled the class. So today we'll just try and go over some of the things that were supposed to be done. I know the TA started with you, but he couldn't finish. I asked him to arrange for an online session. I don't think that has been done as of now. So we want to just use this opportunity to go through the aspects that we did not really touch on. Even though I feel for the composite design, we've been able to do, in fact, the various aspects, but not solve a full question with it. So I'm going to try and solve one question I gave out to students last year, both IDR and main campus. We'll try and solve it and then see how you can approach it when it comes. And the question may differ slightly from yours, but that's the most important thing is you know what you're about to do. That's it. So I quickly want us to go through this example. It's from an exam I set last year to students, and then we kickstart. Can you see my screen? And do you see question number 2 there in the screen?
No. No, sir.
Oh, then I have to share. I thought I've been sharing my screen, so I'm going to share my screen. That will be this. I see my screen now. Can you see my screen? Am I sharing a screen which says?
Yes, sir.
Yes.
Okay, so we want to take a look at this. So what we'll do is that we'll first extract the parameters, then I'll open a whiteboard for us to solve it out. So I'm going to read it out. So we have a figure below, which I'll show you later. And it's a part plan of a composite floor measuring 9 meters by 6 meters. So going down, this is the floor, okay, 9 meters by 6. And in fact, on this floor, there's a beam on grade line 1, there's another beam on grade line 2, another beam on grade line 3. And the distance between the beams is 3 meters. Take note of that. Okay. Then the question says that the slab is to be constructed using grade 35. So take note, please write these things. I don't want to be flipping between the question and my calculation sheet. So take note of all the parameters. I mean, write it down. FCU is 35 MPa. Okay, are you writing it down? Please, are you writing it down or can you hear me?
Yes, we can hear you.
And then the longitudinal beams are of grade. So the beams are still beams and they are grade S355. And the span of 9 meters. So the span between the air starts, this column and that column is 9 meters. Okay, so each beam is 9 meters long. And then it stays at 3 meters apart, like I showed earlier. Then the floor loading conditions is as follows. So thank you. So we have imposed load, which is 4. We have partition load, which is 1. We have weight of finishes, which is 1.2, and weight of ceiling and surface is 1 kilonewton per meter squared. And we also told that the slab is 150 millimeter deep. And then the density of normal weight concrete can be taken to be 24 kilonewton per meter cube. Our first task is to check the suitability of a 356 by 174 by 45 universal beam for beam A2-B2. So A2B2, let's see where it is. This is A, it means from A2 is somewhere here, and B2 is somewhere. So we want you to design this internal beam. Okay? So let's see how we want to check whether if we place this beam of 356 by 174 by 45, it will be adequate. And we have given you parameters that we think might come in handy. For instance, D represents the total height of the universal beam or the depth of the universal beam, and it's 352 millimeters. A represents the area of the steel section given, and it's 57.57 centimeters squared. and T is the thickness of the web, which is 6.9 millimeters. So let's start and solve this. Then we go one by one. So I'm going to move to my other screen. Okay, can you see my calculation screen? Please, can you see
Yes.
my okay?
Yes,
So
sir.
Yes, please.
okay, I don't like this color green. Where is this green color? Okay, so FCU, we're giving us 35 Newton per millimeter squared. Then the depth of the slab, which we are going to call DS, was given as 150 millimeter. Then we're also told that the span of the beam, let's call it L, is 9 meters. What again were we given? Quickly, I want you to tell me the things we were given.
The spaces is the light load 4, then the partition is 1.
Okay, so we have some loads. So we can say live load. Okay, was what? 4 kilonewton
4,
meter squared, right?
yes.
Is there any other load that was given?
And the partition.
Okay, so let me quickly talk about the partition load, because yes, we want to know whether this partition load should be considered as live or dead. But it's a bit, it's more like a controversy normally, whether you want to categorize the partition load as dead or live. But actually, I think it should be a dead load at the end of the day. Even though last year I make them consider as a live load, the partition load is more suited to be a dead load than a live load. So the partition loads are usually the walls which are not structural, okay, or it could be, let's say, a glass, or these days a ceramic or a wooden material, dividing maybe the rooms into smaller divisions. At the end of the day, when these things are there, they will stay there permanently, okay, throughout the whole purpose of the building. Unless maybe there's a regular maintenance, or for some reasons they want to make the rooms bigger, then they will dismantle the wall or the wooden divide or whatever, and then make it more bigger, right? But at the end of the day, it will be there for months and weeks or years. Could be there for years, and then the load is not very like an occupancy load. Like as that today, I'm in the office, I'm not at home, so my load is not there. So hardly does it vary. I mean the partition loads. Okay, it will only vary when, for some reason, there's some service works or some renovation. That is when it will be gone. But realistically, or most of the times, oftentimes, it will be there as a permanent load. For that reason, we are going to make the partition load a dead load. Okay, so we have a dead load from partition. And what was the value, please?
It was 1.
Come again?
1.
1. Okay, what other load do we have?
The dead load 1.2 and 1. As for the ceiling,
Take your time, because I'm listening and I'm not getting you.
1.2.
For what?
I forgot this, but I think it's dead load.
I asked you to go to, is that the only person? Because there are so many people in the class. What was the 1.2 for?
So the finishes.
Was it for the finishes? And do you think it's a dead load? Do you think it's a dead load or a live load?
It's a dead load.
It's a dead load. So plus 1.2. What other load was given? And I think they all have the same units. Okay, the ceiling too,
Yes.
do you think it's a dead or live load?
It's a dead load.
Okay, so 1. And they all have the same units, so I can add. Was it also?
Yes. Yes.
Okay, so the total dead load we have here is 3.2 kilonewton per meter squared. Is there any other load I've left out? If not, then I continue. Okay. So we have this at play. And so we want to check the suitability of a universal beam. And please, what beam are we using? It was 3 something. 3 what? 3, 5 something.
356 by 171 by 45.
45 universal. Okay. So what we'll do is that we'll draw a composite section that will look like this. Then the steel section will come below it this way. So this is obviously the thickness of our slab, DS, which is in this case 150 millimeter. Then we should have a certain weight of the concrete slab to consider, which we normally call BE. But BE actually, if the beams are simply supported, then BE is equal to the minimum of two values. The first value being the length of the beam divided by 4, and the second value being obviously the spacing between the beams. So spacing between the beams. So BE in this case is a minimum of, now the length of the beam was given as 9. If we divide by 4, we'll get 2.25 meters. Then the other parameter we are supposed to consider is the spacing between the beams. If you look at the diagram I showed earlier on, the beams were spaced 3 meters apart. So if I take the minimum between 2.25 and 3, then VE will be 2.25 meters, which is equivalent to 2250 millimeters. And I want to use millimeters because my DS here is currently in millimeters, so that we can work in consistent units. So this is 2250 millimeters. Then we're told that the depth of the slab, the depth of the steel bar, D, if I'm right, was 352. Okay? So with this, we first have to find a way of estimating the moment capacity of this section. Then when we are done, we'll check with the loads coming whether they can take it or not. So with this, we will start with something like finding RC and maybe RS. In fact, we even need to do RW to be holistic. But let's start with RC. RC is given as 0.45 FCU BEDS. And all these parameters, as we speak now, are given. We have FCU as 35, we have BE as 2250, and we have DS as 150. So RC becomes 0.45 times 35 times 2250 times 150. And if we work this out, our answer will be in newtons. Okay, so we can keep it like this, and later we convert to newtons. I don't have a calculator yet, so you do the calculation and give me the answer. But as you do this, convert this to kilonewtons for me and give me the answer.
This is 5315.625.
5315.625. And the opposite students here.
Yes, sir.
Okay.
Yes, please, sir.
Okay. So we have RC there. Then we go to RS. RS, in fact, I've not revised, so I just came for evaluation. So you have to be teaching me today. And as I said, I don't put things in my head. I can easily recall it. So have your notebook around. If I make a mistake, you correct me. So RS is PYA, right? So PY was given as 355, which is a grade of steel. And the area was given as what? I don't have it. What was the area of the steel given from the question we read? The area of
7 centimeters squared.
57.
Yes.
Was it 0.9 or just 57?
It's 57.
And it's centimeters. So what do you think we should do?
Yeah.
We have to convert to millimeters. So we multiply by 10 raised to the power 2. How many of you agree with this 10 raised to the power 2? How many of you agree with the 10 raised to the power 2?
Yes.
Okay, good. So let's solve this. If this will be in newtons, so we take this to kilonewtons and see what we get quickly. Any answer for this, please? We have so many students.
2023.500.
2 what?
023.5.
Okay, some people are chatting. I don't know what they want. Someone says, which question are we solving? We are not going to mind you. Okay, good. So, if we could also calculate RW, I mean, you know why we want to find RW, so that we know whether it's case 1, case 2, case 3. But I can tell you for this question, with RC and RS, it's enough to suffice. It's okay. You don't need to calculate RW, even though I can easily do that. And what is RW? Okay, let's quickly do that. What is RW? RW is PY, then TD, right? But I didn't give the value of the, that's why I don't want to continue. So I'm saying that it's not needed. At the end of the day, we can use this RS and RC to decide whether it's case 1 or case 2. I think case 1 says that for case 1, which we all know what I mean by case 1, RC should be greater than RS. Is it true for case 1?
Yes.
Okay. And is that what we have now?
Yes.
Okay, so it's case 1, right?
Yes.
Okay. If it's case 1, what's the formula for MC? I don't have this software though, so I don't put things in my head. Please take your notes, because I don't want to be flipping back and forth. One person should tell me the formula for MC if the condition RC is greater than what? RS.
MC is equal to RS into bracket D over 2 into bracket D over 2 plus DS close bracket minus in a bracket RS squared DS over 2 RC close bracket.
You want me to put back a line for you? Okay, is it correct? Because this is what I'll use. I'll use this to continue. Is it correct?
Yes.
Yes, sir.
Okay, so we have our RS, we have our RC, we have our D, we have our S, everything is set. The only thing is that when we are working here, we have to be careful. Usually moments are expressed in kilonewton meter. So what I'll do is that as for these kilonewtons up here, I will not change them. I'll use them like we did in class. Then the lever arms, which were in millimeters, I mean those in brackets here, I'll convert them to meters so that I can easily get the kilonewton in meters. So MC will be, I should have invited my Gambian students. They are writing the exams tomorrow. Anyway, they'll be fine. But MC is RS, what is RS? RS is, you said it's RS, 2023.5. Then D was 352. So we convert it to meters. So that would be 0.352 over 2. And DS was 150. So we convert it to meters, 0.15 minus RS was 2023.5 squared. DS is 0.15. 2 times RC is 2023.5. Please, am I right with what I've written?
RC is 5315.
Are you done the calculation or what? Please, I think what I've written is correct. Is it also?
Please say the RC is
no. The RC is what?
5315.5. 0.65.
Point what?
625. Yes.
Okay, so this is correct. Okay, quickly, I'm waiting. Let's find MC, and this will be in kilonewton meter.
Is 601.89.
61 what?
601.89.
601.89.
01.89, yes.
Okay, can anyone confirm? Is that true?
Yes, sir.
Okay. So we have our moments. So we want to see whether, so we are saying that this, if we go for this 2 section, And if it's composite, like there's a composite action, the moment that it can offer is to 601. So we have to check the loading coming onto our structure, whether the loading is greater than this. If the loading is greater than this, then it means the steel we provided is not adequate or suitable. With our hope that what we provide, the steel section we provide will have enough capacity to take the demand coming from the loading. Okay, so let's do that analysis. So we are done with what the steel, the kind of bending moment the steel can hold. But let's quickly look at our beam. So this is our beam. It's 9 meters. So if it's the loading, the whole of this will be 3 meters, because half is 1.5 meters and what? 1.5 meters. Okay, so if we start with the dead loads, we'll start with the dead loads from the concrete slab. So we want to look at dead loads from the concrete slab. So we're told that the unit weight of concrete was what? 24 kilonewton per meter cube. But I'm not going to get the same thing. I'm giving you my question, but you're not going to, it's not the same question as Sam in the others. You'll be surprised. It's not the same thing, but it's something that you have to know your conventions very well and all. But there are things I've done before in class. Okay, I could have made this in kilogram per meter cube, and you should know what to do. Okay, so we're giving this as the self weight of concrete, and this is when it is wet, sorry, it's dry. Okay, so we want to convert this to kilonewton per meter. So because it's meter cube, you have to multiply by 2 distances so that you get per meter instead of meter cube. So this concrete slab has a thickness like this. So this is the thickness. And we're told that the thickness is 150 millimeters, which translates to 0.15 meters. So we have this dimension being 3, and we have this dimension being 9. So 3 dimensions. So if we want to find the UDL as per the unit weight of the slab, what I said in class is that you pick this dimension that is not along where you want to put your beam. We are trying to put our beam the load along the 9 meter span, so that it will be a uniformly distributed load on that 9 meter span. So we cannot multiply this 24 by 9 meter. We can only multiply by the remaining distances, which is 3 and 0.15. So converting this to UDL will be 24 times 3 times 0.15. Okay, so this will now give us a UDL of the self weight of the concrete slab. Quickly, what's the answer?
10.8.
What?
10.8.
10.8 kilonewton per meter. Okay, so that's the self weight of the concrete. But apart from the self weight of the concrete, we also have the self weight of the steel. We now know the steel we want to put there, right? And the steel is giving us this. So what we have to do is to find the self weight of this steel beam. Okay, because we know it. So what we'll do is that this steel beam, usually the weight of it is in the second variable, this variable. So this represents 45 kilogram per meter. That's what it means. Okay, so we are going to make use of this and convert it to kilonewton per meter. Okay, so let's look at the self weight for the self weight for the steel section, which currently is 45 kilogram per meter. So all what we have to do is to convert this 45 kilograms to kilonewton. And we can do so by saying that 45 times 9.81, which is gravity, will give us a force or a weight. And but this weight is in newtons. Okay, if we want to convert to kilonewtons, we divide by what? 1,000. And we now have kilonewtons per meter. So the 9.81 is converting it to newtons, divided by 1,000 is making it kilonewton per meter, so that we are consistent with whatever we have. Okay, any calculation on this?
0.441.
0.441
441.
kilonewton per meter. And please, these are all dead loads. So I'm going to circle this. We'll add this to this. Now, currently, these dead loads are from the self weight of the system. We also have dead loads from the finishes and partitions like we did. And we later said that when we add all those dead loads, we're getting 3.2 kilonewton per meter squared. Not kilonewton per meter, but kilonewton per meter squared. So we also have another dead load. We also have dead loads from partitions, okay, finishes, and sealing or whatever. You know what I mean? And it was currently 3.2 kilonewton per meter squared. So if you want to convert to kilonewton per meter, we multiply by one distance. It being kilonewton per meter squared tells you that it is a surface load or an area load, and it's acting on this surface. Okay. And this surface has distance 3 by 9, right? So because we want to put the UD along the 9, we have to multiply whatever we have by 3. Because on that surface, the other dimension, which is not 9, is 3. So to convert it to a UDL, I'll say 3.2 times 3. And then I'll now have something in kilonewton per meter. What do I get with this, please?
9.6.
9.6 kilonewton per meter. So that, I think, ends all the dead loads I have. I have dead loads from the 3, partition finishes and whatnot. I have dead load from the steel beam, and also have dead load from the concrete slab. So can we add all these three dead loads so that we have one full dead load? So total dead load, quickly add them for me. We have the 3 dead loads. I'm waiting, please. The ones I've circled, they are the dead loads. This one, and that one. Yes, please don't waste time. I'm tired.
20.841.
20.1.
841.
641. Can anyone confirm this?
Yes, sir.
Okay, so we have this is what we will use to do our calculation. Okay, then we go to the imposed loads or the live loads. So as for live load, we just have one. We just have one from here. 4 kilonewton per meter squared. Okay, so to convert it to, even because it's meter squared, it means a surface load. And surface load, it means it's acting on this surface, right? So we can only multiply it by this 3, not the 9. This surface has dimension 3 by 9, right? But we can only multiply it by the 3, not the 9. So we can say to convert to UDL, this will be 4 times 3. And we get 12 kilonewton per meter. Okay? Okay.
Sir.
So then, yes.
Please, with the dead load is 20.841, not 6.
You see, everybody, that's why I asked you. I've not solved this question. I don't solve questions. Please, is it correct? Which one are we using? Is it 8 or 6?
8.
841, sir.
8.
Or maybe she gave me the right one, but I didn't hear out. 841. It should be like this.
Okay.
Okay. So we are ready. Looks like we are ready. Then we now come in, because we are designing, we usually design for ultimate conditions. It's when we are done that we check for serviceability limit states. So ultimate, we have to do our factored design load. And I want you to design as per British standard, which means the 1.4 for dead load and 1.6 for live load applies. Okay. Okay. So 1.4 times 20.841 plus 1.6 times 4, right? Any question on this? Or you're out? Okay. Any question? Or I can continue.
You can continue.
Okay. So you know why I'm multiplying this by 12, because it's the live load. This is the dead load. Answer, please. Please, I need an answer.
48.377.
48.
Yes, sir.
0.377.
Yes, sir.
Okay, anyone with a different answer?
It's the same thing.
Okay. So we are going to design the beam to take this video. So we now have a simply supported beam and the load on it. We now know what is happening. Oh, you know what I'm doing. So 48.377. And this is 9 meters apart. So the maximum bending moment is here and is WL squared over 8. So this will give us 48.377 times the length, which is 9 squared over 8. So let's see what we get with this.
489.817.
489.817 kilometer. Kilometer, right? Anyone with a different answer?
That is correct.
Okay. So the question now remains whether the steel that we're choosing is adequate or not. We now know that the loading from the system, the moment that will be induced, the internal forces is 489. But the steel section we chose had the capacity of what? 601. So I can say that the steel section is adequate. Do you all agree? Do you all agree?
Yes, sir.
Because the steel capacity is bigger or higher than what? The demand, I mean the bending moment developed internal. So it means section is adequate or suitable. Okay, so we are done with part 1. So let's go to part 2. Where is that one? Oh. Yeah, so we are done with A. I just checked and it's okay. And I want you to check the shear capacity. That one is quite simple. Can you see my slide now?
Yes, sir.
You can see the shear capacity. Or I'm sharing that one.
I can see.
Okay. So for the shear capacity, we just have to find the shear forces here and compare with a typical shear capacity of steel section, just steel, because concrete is not good in shear. So we just assume that the steel is often resisting the shear, even though concrete will resist. Okay. So what we'll do is that we'll find the shear force. If this is the UDL, then the shear force at the ends is equal. And I think that one is the FV. I forgot to know. Still a thing. Is that one the FV or the PV? The shear force, the demand. Is that one the FV or the PV?
That's the heavy.
So FV will be WL over 2, right? Okay.
Yes.
So the W was
48.37
times 9 over 2. Quick way, please.
217.696.
696. And this is kilometers, right? So,
Yes,
and you
sir.
also find PV. I think PV was it not 0.6? Yeah, I can be wrong. You are doing it. Was it like this? I'm not prepared for this tutorial because I'm not the one writing the answers. It's you. But is it correct? Check.
Yes, sir, it's correct.
Okay, so 0.6355. Did I give you T? I think I gave you. I gave you small T, right? It was 6 point something. I gave you. Nobody wrote T.
6.9.
6.9. So 6.9. It means all this will be in newtons currently. And then D was 352, right? Please, whatever we have here will be in newtons. So for us to compare with this, when we are done, we divide by 1,000 to take it to what? Kilometers. I'm waiting for you.
The 517.33 kilonewton.
517.33 kilonewtons. Okay? Okay, so we can easily see that what the steel section is offering is bigger than the the internal shear force at the end. So we can say it is adequate. Even though there are some extra checks that I had you to go and do assignment on, and nobody came back to me. I will intentionally put marks there. I gave you assignment to go and do. No one came back and reported on it. Anyway, me, I'll end here. So 517 is higher than this. And so we say that it is adequate in shear. This is just general shear capacity, not longitudinal shear. We'll look at that later on. Okay, let's go to the next one. So you can say section is adequate in shear, vertical shear or whatever. Okay. Then go to the next one. So it says what? Determine the number and arrangement of 90mm diameter by 100mm long headed stack connectors required. So I want you to tell me the number of stacks I need. I also want you to tell me the arrangements, how you arrange it. We are asked that we are supposed to take the characteristic strength of one shear stack to the 104 kilonewton. Okay, so please draw the structural details for such an arrangement. So we'll draw it. So this looks quite simple. So what I'll do is that I have the parameters. I've been told that the capacity of one stack, okay, the nominal capacity is 0.4 kilonewtons. That's the nominal one. But because I'm going to design, then the design capacity usually is 80% of the nominal one. So let's see what is 80% of 104 quickly.
$83.2.
83.2 kilonewtons. So one stack will offer me a resistance of 83.2 kilonewtons. But then I'm not teaching you, we are revising, so I'm going straight. I said that when you get this, you have to then go back and look at your forces, your RC and RS, and check which one you want to use as in your design. And I said that you use the smallest one, because that one will be reached first, or that one will kind of fill first, in that mode first. So let's go back to our RC and RS. This one is strictly RC and RS, okay? So RC and RS, RC, so this is RC, and this is RS. And we choose the smaller of these two. The smaller of these two is what? RS. So we are going to use this 2023 to do the design. So we come here and say that we are supposed to resist 2023.5 kilonewton. But for every stack, you can have maximum of about 83.2. So therefore, the number of stacks needed will be 2023.5 or 83.2. Okay. Anyone? Don't round it off. Give me the answer. I'll round it off myself. Anyone? Yes.
24.32.
24.32. Okay. And they are all kilonewtons, so it's dimensions. But yes, we can round it up to 25 and even 26. We just have to pick something greater than 24.23. Okay. So with this, I'm going to assume that these stars will be arranged in pairs. So if it's pairs, then I cannot round this to 25. Because if I round it to 25, I will not have a complete pair. But I'll just intentionally round it up to what? 26. So I'll say that I need 26 stars. And because they will be in pairs, I'll need 13 pairs of stars. Okay, so 13. And these 13 pairs will span 1/2 of the beam. That's what I taught in class. I'm not going to teach. I'm not teaching. I'm solving a question. And then this, if you say 1/2, the beam is 9 meters. So 1/2 of it will be 4.5 meters. So I can draw just 1/2. Those who want to draw 2/2 too, that's fine with me. I don't have a problem with that. But I'm going to draw just 1/2. This is the center. And for this half, I know it is 4.5 meters. Usually, I know I'll leave a space here, somewhere like this. So this, there will be a space here. I'm going to call A. There will be another space here. I'm going to call that one B. And obviously, the other one would have also continued this way. And it will also have followed the same path. This space will be another B. And this space will be what? Another A. So the question is, determine the spacing S, determine A and B, then we are good to go. Okay, so we are told that we need 13 pairs. So I'm going to work with 13, not 26, because I decided to put them in pairs. So now instead of 26 pairs, I'm working with the number 13 because I've decided to arrange them in pairs. So what I'll do is I'll pick this 4.5 meters and divide. In fact, because I want the spacing to be in millimeters, it will be better to put this 4.5 meters as millimeters. So I'll say 4500 millimeters. Okay, and divide by, yes, there will be, even though it's 13, I can't divide by 13 because if you have 13 items spanning from here to there, the number of intervals or spacing will be 13 minus 1 or 12. Now that's what you have from the beginning to the end. So I have to divide by 12. So what is 4,500 divided by 12?
375.
This is a perfect answer. Perfect answer. Just that if you use that, there will not be any value for A and B, and the two stars will be lining up here. So I don't want to use it. Even though it's correct, if I do that, this thing here will now be here. Okay, so I'm not doing that. Oh, so I would rather reduce this to maybe either 300 or either 300 or
320.
so we can make it 300 or 325. 350 will not be too.
I
Let's
said
make
320.
320. You want us to make it 320?
Yes.
Okay, so this one, if you are the designer, so whatever you choose, I'll mark. Okay, but it should be reasonable. So 320, right? If 320, then from here to here, we'll now have 12 times 320. Okay? Okay, so what do we have?
Yes, sir.
So this will give us those calculating.
3840.
3840.
3840. And if we choose 320, usually this B here is half of the spacing. So this B will be half, which is 160. This is also another one, 160. So B now is what? Usually it's half. You should know this by now if you're solving a lot of questions. Okay, so we now have this gap as 3840. You also have B as 160. So calculating A will not be a problem. A then will be the total length, which is 4500 minus 3840 minus 160. So what is A? That will be A. If you look at what I've drawn, that will be A. So what is A?
500.
500.
A is
Sir.
too big. Oh. Yes, A is too big. Oh.
Sir, please, I have a question.
Yes, what's the question?
Sir, when we find the number of stars,
Mhm.
we use the force over the design strength.
Mhm.
So you said that we should take for the force, we should take the minimum value.
Yes.
So I was thinking that because the force will be governed by where the neutral axis will lie.
This, I'm not in class, please. I'm not explaining this again. If you like, do what I'm not going to explain this. I've explained this in class. Somebody can teach you. There's a reason why I said that. I'm not
Okay.
doing it. Ask your friends, those who are still side with me. I gave a reason why we choose the minimum one in class.
Okay. Okay. Thank you.
Mhm. Or who can explain it to him? Who can explain it to him? I gave a reason for this. Hey, no one. I'm stopping the lecture, so I'm going home.
Oh, sir.
Uh-huh. Yes, explain why he's asking why we were using the smaller one and not the bigger one. So with those, unless you have not been following. Oh, this girl, she wants to join me. I'm waiting for you. Yes. In 5 minutes, if I don't hear anyone explaining this, I end the session.
Please, we do have a question.
My good friend, ask your question again.
So I was saying that when we're calculating for the number of stats, you said we should use a smaller value between the RSN and RC.
Mm-hmm.
And I was asking why not by where the neutral axis lies. So you said you told them why in class.
Yes.
Yeah.
Did you get his question?
Yes, sir.
So answer. Is your question related to why the minimum or the question related to the neutral axis thing?
What kind of book on about implications in an the
My good friend, I'm saying is a question relating to whether to use the maximum or the minimum or
Yes,
not
I
where
was.
the
So my question was I was thinking that maybe to select the force that you use, you have to check where the neutral axis will lie.
Oh no, you don't do that because why are you putting shear stats?
On the
Yes.
beam.
Yeah, you are putting shear stats. Why? So that
Yeah.
so that you can connect the steel and the concrete so that they become one unit. And when
Yeah.
you do that, we have something called a full composite action. A full composite action where we will be able to reach our design moment, which was 601 kilonewton. We don't want the thing to fail in shear. So we have to get up to that capacity it can hold. We want to utilize that full capacity. But we can utilize it when there's no failure or the concrete and the steel section does not slip. We don't want them to slip because when they slip, then when they slip, significant slip, then they don't act as one unit. So it's like concrete is separated from the steel. But why do you think slip will occur? Slip will occur at the interface of the concrete slab and then the steel section. That's where it will occur. If there should be slip right now. And that place is what we are considering an RC. That place is not the neutral axis. Where slip will occur, it's not the neutral axis. So we cannot be designing shear capacities at the neutral axis of the whole thing. I don't know whether you are getting me.
Yeah, so you're saying that where the slip will occur, that's where that's what
Yes. Yeah, that's what we have. That will govern because that's where we don't want the slip to occur. So technically, that interface becomes our neutral axis. Because if the slip will occur at that point, okay, then we don't want it to slip at that point at all. Okay, so we consider the force for concrete, which is the one above that interface. And then the one below the concrete, which is the steel. And we say that these two materials, which one will slip first? Which one will slip first translates to which one is minimum. If it means that there will be that one will govern the whole slip action. But if we put it at the neutral axis when we're designing for the movement, it could be inside the steel. And that one, there's no slip inside that steel section. That part cannot slip. Let's continue. So yes, I'm saying this 500 is too much, and none of you could explain this. I'm going to I'm going to find a way of deducting mass on your exams. Yes, I said this 500 is too much. You're 320. Can we do something about it? Unless this
we can use
500.
350.
I'm not saying
So
it's
let's
wrong.
use 350.
What? Which one?
Just move this to you.
We should use what?
350.
350. Madam, I'm not saying it's wrong, but you can ask them to details, correct? But I think that 500 on one side is too much. You might as well need to put one start there instead of to get 20 at 14 pence, which is correct. I'll still mark it if you do that. Okay, they say they want us to use 350. If 350, then we'll now have 12 times what? 350, right? Okay, and what do you get? Oh, hurry up. Oh.
4,200.
Then B will be what? I gave you a formula for B. B is what?
175.
175. Then what will be A now?
125.
Yeah, this looks nice. So and you said the answer is what?
125.
Okay, it looks nice. Okay, it's okay. We'll take this one. So the arrangement, you draw this one. And you say from here to here. That one, you draw it nicely. You say 13 pairs at 350 center to center. Then 175, 125. Okay, center line. Okay. So you are done with C. Can we continue to the next one? Okay. So D. This is assume the slab is reinforced in both faces, means top and bottom. With T10. T means high tensile, 10 means diameter of the bars is 10 millimeters, and they are spaced at 150 millimeters. Check the longitudinal shear capacity of the concrete. Okay, so we are going to see whether, in terms of longitudinal shear, is adequate or not. Usually using two failure planes. Okay, so we now have, I don't want to draw, but you should know it. We normally take a meter of the concrete slab. Then we know that there will be some bars here. I don't know the number of bars. I'm going to calculate them. Then we need some ACV and ASV because those are the key things. And they will be different for different failure planes. So we can start with this failure plane. I know you remember AA. The AA was the vertical one. And in class, I was doing only one-sided A, not the two-sided. Okay. The two-sided was what, those in Kumasi, one guy was saying that we should also look at that one, but I'm not doing that. We can also check it. But let's do the one-sided AA, okay? Then for that one, I think I gave you formula for ACV. And I said ACV will be
1,000 DS.
Do you remember?
Yes.
ASV, I said is AT
plus AB.
Okay, so we can start with that one. So let's get ACV. ACV is 1,000, DS is 150, right? So this will give us 150,000. Okay, this is millimeter squared. Hey, as for ASV, we need 80.
I just see no reach that point yet.
Oh, I was disturbing her. Okay. So 80 area for the top. We have to find the number of bars within 1 meter. Okay. We were told that these bars were 10 millimeters. The diameter was 10, and they were spaced at 150. Right? Was it not 150? The spacing.
Yes, sir, 150.
So we'll do 1,000 for 1 meter. This is 1,000. Then we divide by what? 150. But this one as this to get the number of bars. I'm still not. And this one I said when you finish, you subtract one in class. In fact, we should have rounded up. But because we want to be conservative, we take it down instead. Okay, so what is this answer?
6.67.
And we said we'll use 6. Do you remember? If you don't remember, that's it. So it's 6. So we are going to use 6 here. We also use, and the same top bars was given for the bottom bars. So A top will be simple. I just need the area of 1 bar, then I multiply by the 6. So pi d squared over 4 times 6 will give me A top. The diameter of the bar was 10 millimeters. So I do this over 4 times 6. So this is for 1 bar, then times 6 for the 1 meter I've considered. What's the answer for this? A top.
So please, for 1 is 78.54.
So times 6 will be what?
471.24.
Millimeters squared, right? And because the same bars for the top was given as the bottom, we don't need to do any calculation. This will also be like this, right? To be the same thing, I told you that use the same bars. Okay?
Yes, sir.
So ASV for failure pin AA will be 471.28 plus another 471.28. So ASV will be what? Answer, please. 2 times of this will be what?
942.56.
So now I have the areas. I can work out for AA, then later we'll go and work for the other one. Or do you want me to get the AS and ACV and ASC for plane BB? Or we should finish solving this? Then let's finish solving this. Okay. So how did I call it? Was it VR? I've forgotten this. But I know what I'm doing here. What if it's VR? What's the answer? Was it 0.7 or something? What's the formula for the capacity?
The capacity.
Yeah, for there was longitudinal shear capacity, and you compare it with the demand. The capacity side, what the formula? Something times ACV, was it 0.07 or 0. I forgot to know, I'm not revising.
0.7
0.7 what?
ASV
ASV.
FY. Yes.
That's
No,
all.
if it's 0.8, that's this one. No.
No, it's this one. This is the capacity. This is
That's
what
it.
yeah.
0.7 ASVFY
Mhm.
plus 0.03 N
And
AC
Or
ACVFCU.
and this is one, okay, because I didn't say anything about electric concrete. So the VR will be 0.7. ASV was 942.5. For FY is high yield bar. So let's make it 460. Okay, plus 0.03. ACV, we got 150,000. And FCU was what? 35, right? Okay. But this force we'll get is in newtons. It's in newtons because this is in Newton per millimeter. So everything is in Newton. So what we can do is that we can convert this to kilonewton. Okay. So what is the answer? Please solve this and give me the answer. For this will give us a force. But we'll assume that this is the force considering a meter of the slab. Hey, please solve this. I want to run away.
Wait. Yeah, talk on. Yo, Lucifer, they can. So
Yes, what's the answer for this? Are you calculating?
Yes, sir, we are calculating.
Oh, today you are very slow.
361.
What?
461.
461.004.
What forward?
61.
kilonewton, right? But this is after we considered a meter of the slab. You can leave it like this. Okay?
Okay, yeah, 461.004.
It's the same thing. It's the same thing. Oh. I'll take it like that. The thing will not even pass, and you are wearing the calculation. It's okay.
Even pass.
Continue. Okay, so this is the capacity, right? We can take currently our concrete slab in terms of longitudinal share can take 461. But what is coming? The demand, I think was NQP over S.
Dr. Jack, there is a limiting value that it has to be compared with.
Yes,
And
yes. What's the
0.8 meter ACBFC.
0.8 what? Okay, the limiting value.
0.8 meter ACV root FCU.
Okay, ACV. Listen like this.
You forgot the
N that is between 0.8 and ACV. There's an N. The one that you said is naturally 1.
So this, I think this was the formula. So N represents whether you are putting them as single or in pairs. We said we put as stars as pairs. So N is 2. QP was the design capacity of each star, which was 83.2, and this kilonewton. And the spacing was it 350? Hello.
Yes, sir.
Yes, it was
Yes,
1050.
sir.
Yes,
So
We can hear you.
Hello.
Millimeters. So
Muted out.
the meeting complete. So 2 times 83.2 over. Then we convert this to 0.35 meters, so that it has similar units as this. Okay. So let's solve this out and give me the answer.
475.4.
For what?
75.4.
Oh, we're not lucky at all. We're almost there. Oh. So it is not adequate. Can you see that it's not adequate? This is the demand, and this is the capacity. Okay. So you leave it like that. Or if you can suggest ways of making it adequate. From the answer you've given me, I've not solved it. This is what you are saying. Is that clear? Please, is it clear?
Yes, sir. Yes, sir.
Yes, sir.
We were discussing how to even make it increase, finding ways of making sure it's adequate. So you suggest all that. I'll mark. Then let's do BB. BB was quite simple. BB, oh, I'm not drawing it, but the shape looks like this. I think this was 7 times the shank diameter. Do you remember this? And this, if it's 100 millimeters, we are assuming that we've lost 5 millimeters from welding. So we make this height 95 millimeters. I'm teaching as if you've revised it before, so I'm not going to explain what I'm doing. You should know this already.
So we didn't do this. So we didn't do this in class.
Is it Obasi or Kumasi?
Please, we did it. Why? We did it.
Please, Obasi, we did it. Yeah, so ACV, we did this in class. We did this. Did you do
Yes, done it.
Yeah, we did. We have done it.
Even Obasi, right?
Yes, sir.
Why are you disturbing me, please? So ACV. I give the formula for ACV. ACV will now be 2 times 95, because we have 95, 195, 195, plus 7 times 5. Then this is, yes, what's the problem?
That's it. So I said the demand, we can reduce it by increasing the spacing.
But if you increase the spacing, it will still be, you can still, yes, if you increase the spacing, there will be an implication on the ASV and ACV.
Yeah.
Because if you reduce the spacing, what will happen is that it will affect something. So it's not as simple as that. I just want to quickly check. it will affect.
It will affect
Then maybe the A and the B and the A and B will
ASB will be
change.
affected.
What I want to change? It will affect something. It's not straightforward like this.
It will affect ASV because the area at the top and the area at the bottom might increase or decrease.
No, ASB has to do with the rebars.
Yeah.
It's not the spacing.
The A and B that will change.
The A and B will change, but if you increase the spacing, your A and B will change, right?
Yes, but that one they don't
And you see, the problem is that we cannot easily increase the spacing because the spacing we normally bring it down. You see, we have 375. We are not going up. We couldn't go up again. We're rather bringing it down. I don't know that getting me.
Yeah.
So you cannot easily increase it. Okay, it's part of the revision up to Thursday. Go and play. Let me solve this. Let me go. It's part of go and think about it. But you cannot do that. You cannot increase it. Rather, you have to be dropping it. Is it clear? That part of what I'm saying.
Yeah.
You cannot do what. Okay, quickly. This is times 1,000. Then ASB, I said, is 2 times AB. Do you remember? Those who are in class. Do you remember this thing?
Yes, please.
So the diameter was 19 mm, right? So ACV will be 2 times 95 plus 7 times 19, then times 1,000. 1,000 for the 1 meter. And this, what is in the bracket is a perimeter. Okay, so what is ACV? Yes, those calculating. What is ACV?
323,000.
Like this. How many zeros?
3 zeros at the back.
Okay. Then ASV is 2 times. Oh, it's the same as what we did because the bottom and top are the same set of bars. So this is the bottom one. It's the same as what? The top. So I'm just going to pick it up. 471.28. I think we'll get the 9 something again. We'll still get back the 9. What did we get? 942.56 millimeter. So the calculation is now simple. So VR was 0.7 ASV FY. Check if I'm wrong. Am I correct? Plus 0.03 something ACV FC. Okay, so this is the form. So this is 0.7. ASV is 942.56. ACV is 416. Then 0.03. This is 1. So then ACV is 323,000. And FCU is 35. Okay. So when you finish, you convert this to kilonewtons. Okay. And this will be the force per meter of the slab, the beam. Is Ali in class?
Yes, sir.
I'm calling you. Your phone has been busy since 1 p.m.
Yeah, I didn't have lights.
No, your phone has been busy. Says busy.
Yeah, you block you.
Yeah, block me. Ali, you block me. Because I've been calling you.
But sir, I called you.
No, I've been calling. I try calling. Number busy. Who are you talking to?
Network.
And then is the
You and Jude, I was calling the two of you. It wasn't going through.
Yeah, he begs.
Okay, who was the answer?
It's network 6426.58. 642.65.
So this is kilonewtons. And this is after we considered a meter of the slab, right? So per meter.
Yeah.
Okay. As for the V, it will not change you. And QP over S, it will not change you. It's the same thing, right? We've solved this. You remember we solved this? Hey, it's this is it. This one will not change. This one will not change. Hey, but you didn't talk about limit, whether it's greater than a limit or not. This your answer. Did you check with the limit? And which are we using? The limit that Jude gave, I even forgot about it. There was a limit that this should not exceed. What's the formula, please?
Yeah, 0.8, the N value ACV, square root of FCU.
Okay, so let's check the limit. 0.8,
N value.
N value is 1 in this case.
Yeah.
30,
ACV,
35.
square root of. Yeah.
What's the answer? Well, yes, answer the boys. Only 103 students. Good.
1528.715.
1528 points. Did you convert to kilonewtons? Did you convert to kilonewtons? Okay, then
Yes,
it's
please.
fine. It means this is for, we'll use the 6 point, whatever kilonewtons. We'll use this one, right? Okay. Now, the N over NQP over S will not change. N is still 2, QP is 83.2, and this is 0.35 for what we did, right? So we got something like what's the answer? 475, right? Yes. So 475 point whatever. So because the demand, this is the demand, is less than this capacity. Then as for this plane, the longitudinal shear is adequate. In this plane, it is okay. The only problem we had was the other plane, the first one, the AA. This one is where we have problems. So you go and you fix it yourself during the exams. But this one is okay from what we have here. The demand, which is 475, is less than the capacity. Any question? Okay, no question. So we go back to my slides. I want to share the idea of the one I gave to student last year. So I'm going to share right away. I know some people are taking pictures and all. It will not come. All this will not come. Yes. Okay, so we've done this. Okay. So we have been able to check the longitudinal shear. The last question, then we call it a day. In fact, last year I just asked them to calculate the impose load deflection, but yours will be different. There was one lecture I showed you how to check the serviceability limit states. Do you remember? We saw variable load, occupancy. Do you remember that thing?
Yes, sir.
Yeah, we can't do it today, but I thought I will use 1 whole 2 hours to teach that. So your question would be different. Now check the adequacy of the whole composite beam in serviceability limit state. I solved it with you. It was very simple. We add a variable to the what do you call it? The composite action on prop construct. Is it prop or on prop?
Execution stage.
Execution stage and those things. Do you remember?
Yes.
Yes, we
And you
did
understood
execution
it.
and composite stage.
Oh, you know it. So all that one will come. And we calculated I using the parallel axis theorem. Do you remember?
Yes.
Yeah.
Yes. It's the same thing. So just imagine that I want to do this right now. Go and do it in the house. You can easily do it. But I gave you a 2 hours lecture on it, so I don't see the difficulty here. We can solve it right now, though, but I want you to go and try it out on your own. What do you think?
Okay.
It's not any difficulty. It's only the I, calculating the I, doing the execution stage. That you have to use parallel axis, find first moment of area, the second moment of area before you get it. Those in the class, they write it down one too.
Yes, sir.
You remember? Yes, 2 hours class. So that will be, it will not be like calculating post load. No. I gave you 2 stages. We did this and we add, then we check whether it's greater than 360 or not. Length over 360 or whatever. It was a whole set of questions. Okay. And so that is it.